4 days. I had previously packed it into 3 weeks, and that's what this book was about. I gave up a series of lectures at PCMI, and those are the notes that came out of that course. I'm going to be lecturing mostly out of that book, and in particular chapter 2 is going to be the bulk of it, and then some chapter 5. Chapter 1, I also included links in the website to chapter 1, 2, and 5. There are PDFs, so you can read them. I also point out to examples and exercises from there. But basically, this is a tour of what's there, and then I strongly suggest you take a real course on elliptic curves, a graduate level course on elliptic curves if possible. I have actually added also, if you go to the website, so if you go to the thing about lecture A2, so I've started to build some set of links in here, but in particular there's a set of links to references, books on elliptic curves. As everyone will tell you, the Bible on elliptic curves is Silverman's book. So this is the book you want to read eventually. Whether you're there or not, that's your goal, is to read that at least 10 times. So we're going to try to get you there, that you're at least interested in opening the book. Once you start there, I think you won't stop. Okay, so let's get started. So what is an elliptic curve? The elliptic curve over Q is a curve given by an equation of the form y squared equals x cubed plus ax plus b with a and b rational numbers, and we are actually going to make sure this quantity is not 0. Okay, so now if you've never seen an elliptic curve before, you look at that and it seems like very oddly specific definition. Why these curves in particular? Why are so many people interested in these particular curves? So they're recording this, so let's rewind and start from the beginning. Why elliptic curves? Okay. So I'm not interested in elliptic curves per se. I'm interested in all Diophantine equations. Okay. So from the time of Diophantus of Alexandria, from where that name comes from, there are many problems that are very easy to state in number theory that end up in some polynomial equation with integer coefficients, and the solution is there. And you have to find what are the possible integer solutions to some equation. So there's some Diophantine equation like this, where f is some polynomial in a number of variables. So a polynomial with integer coefficients. And I'm interested in solving this equation. And by that I mean 2 questions. I want to know, I'm going to call this C, and I want to find what are the integral points and the rational points. So I want to find all the integer solutions, the solutions with integer coefficients, and also all the ones with rational coefficients. And Diophantus, back in 2,000 years ago, he wrote several volumes of problems like this. His whole book where that Fermat was reading when he started writing his book and writing in the margins. Well, what Diophantine does is like, here's an equation, here's how you solve it. Here's an equation, here's how you solve it. Here's an equation, here's how you solve it. And they are all equations of this form, and he's giving you tricks. Just it's like compilation of the greatest hits of tricks to how to solve the Diophantine equation. So let's see where we are. Okay, solving the Diophantine equations. There are two variables here, sort of in the study of Diophantine equations. There is one right there, the number of variables, and there's another one that is hidden here, which is the degree of f. Okay. I claim that all of number theory is this, is solving Diophantine equations, and you'll see why. How many of you have had an elementary number theory course? Many of you. So what's the first thing you learn? What was the first chapter? Linear Diophantine equation. So you said units? Division. Just learning how to divide the Euclidean algorithm, but also just like divisors, okay, of numbers. So let's start with. We'll see how that all comes up in here. So with n equals 1, if you have just one variable, then we are talking about f of x equals 0, where this is a polynomial, and this is so something of the form an x to the n plus a1x plus a0, where these are all integers. And you can prove, and you've probably proved before, that we know how to solve that. We know how to find all the integers, the integer solutions, all the integral solutions, all the rational solutions, because it's easy to check that if, say, P over Q is a rational solution, then what happens? P is going to divide A0, it's probably not even only F, it's just this happens. And Q divides AN. Right? So that gives you an algorithm, because I can factor A0, I can factor AN, and list all the possible prime divisors that appear in one side or the other, and I can just make up all the possibilities and check what are all the rational solutions. So this one is, we know how to do this. This is easy. Okay, so let's move on. This was for any degree. Great. Okay. So far, so good. So what about n equals 2? So n equals 2 now we're talking about a polynomial in two variables. So it's a curve on the plane. So let's start easy on us. The degree of f is 1. What is that? Then c is ax plus by is c. Okay, and let's just assume, so it's not one variable, that a and b are not 0. Okay, are there rational solutions on the line? There's always rational solutions. You can take x to be any rational number you want and then solve for y or vice versa. Okay? So over q, there are infinitely many points always, and you just solve for one variable in terms of the other, and you parameterize all of them. 5 more minutes. 5 more minutes. Okay, so over q, infinitely many points always. How about over z? So this is what you said was one of the first things you learned in an elementary number theory course. How do you solve that? That's a linear Diophantine equation. you learn how to do Euclid's algorithm, you go backwards in Euclid's algorithm, and you solve what's called sometimes the Zuse equation. That's that. But to solve that, you actually have to develop your whole theory of divisors and your whole theory of GCDs, and then Euclid's algorithm comes in, and so on and so forth. So there's all the theory of divisors, the theory of GCDs, all of it put together tells you that there is a solution over Z if and only if the GCD of A and B divides C. Okay? So there is a solution to the problem of how to find integral points on a line. And this can be quite surprising at first that, so this is an exercise for you, so you remember how to do that. Find all the solutions, all the integer solutions of so two lines that are very similar, they end up having completely different behavior, that one will have infinitely many points and the other one will not because of this. Okay, so you can try that out. All right, so we're done. Within 2, degree f is 1. Let's move on. How about n2, degree of f is 2. Well, now your curve is a conic. Okay, I'm going to be skipping singular cases. If your quadratic polynomial is singular in some way, it basically is the product of two lines. Okay, but you can reduce it to the case that it's the product of two lines, and we know how to find solutions in each line. Forget about it. So I'm going to look at curves that are smooth, and that will be a conic. Okay, so C now will be something like this. And the integers is a little difficult, but even over Q, this is already a very subtle issue, whether there's a point over Q, and it had to wait for thousands of years for somebody to come up with a method to tell whether there is a point over Q or not, given one conic. Okay, so what we see here is already a fascinating area of number theory, which is called local to global principles, which is one of the titles of one of the courses here. So over Q, we find an example of local to global principle. Which is called the Hasse principle, or the theorem of Hasse-Minkowski. And what does it say? It says that if there are points locally, then there are points globally, and vice versa. What globally and locally means here is the following. So the theorem says that C has a rational point if and only if Okay. C has a Q rational point if and only if C has points locally. And locally means here, like locally in the real numbers. If you look locally at a local interval, are there points in there? If I find points, then there are points locally. But there is more to local. Like in several courses today, you've already heard about the p-adics. The p-adic is another way to study the rational numbers. So we're going to look into all the possible ways that we can zoom in into the rational numbers in the reals way and then in the p-adics way. So if there are points over the reals and over QP for all P, then there is a rational number and vice versa. So this actually, there's an appendix in my book about a very short introduction to the p-adics. But you will learn more. I think there were a lot of promises being made today, and people were going to do this and that later on. But I think Liang in particular said that he will do some more of the p-adics tomorrow. You can see like a 2-3 page introduction to the p-adics over there. For now, if you've had some elementary number theory, it just says that there are solutions modulo p to the n for every n. Okay? So solutions, more or less, is solutions modulo p to the n for all p and all n. Okay? So if there are solutions modulo 2, 4, 8, 16, modulo 3, modulo 27, modulo 81, modulo 5, 125, and so on and so forth, that's all the powers I know, then there are solutions over Q. This seems like a daunting task to check this. It seems like this is an infinite condition. I'll never be able to check this. It turns out this is not so. You just have to check. If you multiply all the coefficients together, look at what primes are there, that is, those are the primes that you actually have to check. So you have to check that, and you don't have to go much farther than modulo 8 and then modulo p for every other p, basically, in here. So this is something that you can actually do, okay, and check fairly easily. And then it tells you, yes, there is a point. And then you let a computer run, and it finds it for you. Okay, so that basically solves in a very, very surprising way, and a very, well, not surprising, but it's something that we would hope for, that basically these somehow encode all the arithmetic prime by prime, this encodes the real arithmetic, and if everything works out, then there should be a point there. How else would it work without there being some sort of like, this is what we call global, so some global shadow of a point. These are the shadows at every completion. If there is a shadow everywhere, there must be something making a shadow. Okay? So, for instance, if you look at conics, this has no points because it fails in the real numbers. No real points. Okay. What about this one? This one has real points, right? The square root of 3, 0 is 1. But there are no solutions modulo 4, so there cannot be integer solutions, for instance, and that creates all sorts of problems, so there are no rational solutions either. So mod 4, it fails. What about this one? Well, that one, there are over the reals, there are solutions modulo 4, because 113 is 1 mod 4. And if you start checking, there are solutions modulo everything. So where is the point? Can you see a point?
I don't think it's possible because it's 43. Oh, sorry, it's 164 and 49.
Yes, it is possible. Okay, yes. so there are solutions over R. You can check that there are solutions over every QP, and Hasse tells you, like, okay, go ahead and look now because there is one. Go and find it, and you can find it. It turns out x equals 7, y equals 8 is the solution. 49 plus 64 is 913. Okay, very good. All right, I have 1 point. Are there infinitely many points over Q? That's the easy part. Once, you were saying it very emphatically. What do you think?
Yeah, right. You just project from that point onto a line.
Exactly. So now it's the easy part. Finding the 1 point, whether there is a point or not, that's terribly difficult. But finding all of the other ones, that was known long ago. So, so once you have this, so this is a circle of radius, the square root of 113. We have 1 point somewhere here, and now what I can do is parameterize, but say by just draw a line like this, and by the slopes of those lines, give me points of intersection, and those points I claim they're also rational numbers.
These 3 lines?
What is it?
What are those 3 lines?
These are, so this is my point, my given point 7, 8.
Sure.
And then those are just lines where the slope is rational.
Okay.
Okay.
Sure.
So I can perhaps what you can do if you want, you can put the origin of coordinates in here if you want, and then they're just y equals tx. Okay. And then move them around, find points of intersection, and because these lines have coefficients over the rational numbers, when I intersect with this, say I put it here y equals, I don't know, 2x plus 1. Then this will give me a quadratic equation, but I know there is already one rational solution, so the second solution has to be rational as well, and that will give me an x coordinate that is rational, and the y coordinate is just a linear combination of that one, so this is also rational. Okay, so you can play with this. So these are new points. So if you see, I suggest you, if you've never done this or you are rusty, that you do exercise 2.12.2 in the notes, where you do some parameterization of this sort. And the thing is that this whole stereographic projection, and you get every point. You get every rational point on this circle will be one of these. So you can go both ways. That if you do a line, the intersection is rational. If you have another one, you do the line, and you see that it also comes from this construction. Okay, how about over Z? So the integral points is another very typical chapter in elementary number theory books, which is Pell's equation. Basically, over Z, any conic, you can reduce it, you can complete squares and do a bunch of transformations that reduces the problem to finding points on Pell's equation, something of this sort. Something like that. And there are several methods that have been found to solve Pell's equation. For instance, I don't know how many of you have know about continued fractions. Okay, so using continued fractions, you can actually find solutions to Pell's equation and find all the solutions to Pell's equation and so on. So I'm not going to go into that, but basically we also know how to find the integral points on conics. By the way, if it's a circle like this, you don't have to go that route. If it's a circle, then, well, it's just, there's only finitely many possibilities for x and y, you just check them all, or do some congruences, you can see, you can do a bunch of things, but it's a finite computation. This is the Pell's equation comes when, so the conics can be classified into ellipses, parabolas, or hyperbolas. The Pell's equation is the hardest one, is the hyperbola case. The parabola case, the circle case, those are easy to parameterize. Okay, the point being, we know how to do also for quadratic equations, but there's a whole very rich theory that was created just for each one of these cases, which is the stables of number theory. Okay, so what about the next step? Where were we? N equals 2, degree f equals 2. Okay, humanity is doing very well so far. Okay, so what about cubic equation? So C is now a plane cubic. So it is something like this. I'm not going to write all the coefficients now. It goes something like this. Okay? So this is a very interesting case because unlike the previous cases, when we had one rational point, we had infinitely many of them. And we had both. There are sometimes no points, no rational points. That implies no Q points. Okay, so there are examples where there are no rational points whatsoever. But in this case, there are all possible flavors come into place. That there are, there can be no Q points, only finitely many, but finitely many being positive, so a few. Finitely many points, or infinitely many points. Okay, so it's the first stage where things become really interesting, that there is the whole array of possibilities that can happen. But the bad news is that here's where the humanity has stopped. We don't know how to do it. Essentially, we don't know how to solve this either over Q or over Z. We're stuck. So, so here's the bad news. The bad news is that this ideal world of Hasse and Minkowski, where we were seeing shadows, and there's shadows, there's a tree. Now we see shadows, and sometimes we see nothing. There's something casting a shadow that doesn't exist over here. Okay. So what happens is that the local to global principle fails, and we don't know how miserably. That's one of the conjectures of the field. That we hope is not too bad, but it fails. So the local to global principle that we know that it fails. So, so there are cubics that have solutions over R over QP, but there are no Q solutions. Okay? The first such example of such things is called Selmer's example. It's 3x cubed plus 4, y cubed equals 5. That has such a property. There are real points, there are points over every QP, but there are no rational solutions. So that's very tough news for us, because that was such a good method to find at least some computational method to find whether there are points or not. And the bad news keep piling up, which is that this also fails to some degree. That if I have one solution, can I find all the other ones? No. So we do not have an algorithm to find the Q rational points on C, even if we know one point. Okay? So this is the frontier of the theory of Diophantine equations, and this is elliptic curves. This is why we're interested, because a cubic equation, a cubic plane, plane cubic with at least one point, that is an elliptic curve, a non-singular plane cubic. So a non-singular plane cubic C with at least one Q point is called an elliptic curve. That's great. So, but I started defining elliptic curves in a much more concise way. There was this very short, neat equation, and now we're saying that every cubic like that is an elliptic curve. We'll get to that in a moment. But let's just like, okay, this is very depressing. Can we move on? Maybe this is a very bad case, and we know how to do the rest. The rest is just a mess. And I'm not even saying n equals 3. It's n equals 2 and higher degree. That is even worse. So I'm actually going to put 5 here because sometimes some plane cubics with degree f 4, those are also elliptic curves. So the thing is that beyond what you realize at this point is that you've been looking at the wrong invariant. The degree of f is not the right thing to look at, is the number of holes this curve has. Oh, what are you talking about? So what we're going to do now is that we were looking at our curve, we were looking at over Q, sometimes we were looking at it over the real numbers, right, to see if there were points, but look at it over the complex numbers and let's see what it looks like over there. So if you go back, if you go all the way to the complex numbers, if your curve is given by a polynomial, it's non-singular, then it will give you what's called a Riemann surface. So it's some nice